Chapter 9, Section 11, Completeness and Hilbert spaces. In this section, we will explore how the concept of completeness helps us ensure that Cauchy sequences remain within a given space, especially in infinite-dimensional settings. Why this property matters for mathematical analysis. How it enables the rigorous use of approximation methods. By the end, we will see how combining completeness with inner product structures leads to the powerful and foundational concept of a Hilbert space. So, why are Cauchy sequence and completeness important? Let's consider a familiar example, three-dimensional space, R3. This is the space where any point can be expressed with three coordinates, x, y, and z. In such a space, every Cauchy sequence converges to a point within a space. In other words, the sequence's destination is guaranteed to be inside the space. That is why, in basic linear algebra, we generally do not have to worry about completeness. However, things change when we deal with infinite-dimensional spaces. Let's consider the following sequence of polynomials. As we add more terms, each polynomial, f and x, approximates the sine function more and more accurately. That is, the sequence of polynomials is a Cauchy sequence that converges to sine x. However, sine x is a function that can only be represented by an infinite number of terms, and no matter how close a polynomial gets, it can never become sine x itself. Therefore, no matter how well you approximate sine x within a space of polynomials, the destination of that approximation lies outside the space. So, why is this a problem? If you were solving a problem within a space of polynomials, the result will end up outside the space, although it gets arbitrarily close. It means the solution does not exist within a space. This is a serious issue in mathematics. For example, infinite series may lose their mathematical meaning. The results of iterative methods or approximation techniques cannot be treated correctly within a given framework. This is why completeness is essential. In a complete space, if a Cauchy sequence converges, its limit is guaranteed to remain within the space. This ensures that analytical techniques can be used safely and reliably. To avoid such problems, we use a special kind of space called the Hilbert space. Now that we have seen why completeness is such an important property, let's put everything together and introduce one of the most important structures, the Hilbert space. A Hilbert space is simply an inner product space that is also complete. We already know what an inner product space is. It is a vector space where we can define angles, length, and orthogonality using an inner product. But that alone is not enough if we want to work with infinite sequences or continuous functions. We also need a guarantee that Cauchy sequence of vectors, like an infinite sum or series approximation, converges within a space. That is what completeness adds. So, when a space has both properties, geometry from inner product and convergence from completeness, it becomes a Hilbert space. To understand what a Hilbert space is, let's walk through two classic examples, one finite-dimensional and one infinite-dimensional. We will highlight not just definitions, but also the logic that makes these spaces Hilbert. Let's start with the finite-dimensional Euclidean space, Rn. Rn is the space of all n-dimensional real vectors. For example, a vector in R3 might look like this vector. This space comes equipped with the standard inner product, which is defined in this way. This inner product satisfies all the axioms of an inner product: linearity in the first argument, conjugate symmetry, positive definiteness. Also, Rn is complete, meaning that any Cauchy sequence of vectors in this space converges to a limit that is also in the space. Because it has an inner product and is complete, Rn is a Hilbert space. Let's consider an example of an infinite-dimensional space. The space L2 consists of all infinite sequences of real or complex numbers. However, not every infinite sequence is allowed. The defining condition is that the sum of the squares of the entries must be finite. This condition ensures that the sequence behaves nicely. It does not blow up in terms of size. This also makes it possible to define geometric concepts like distance and angle. Just like in Rn, we define an inner product between two sequences, xy, in this way. This inner product again satisfies all the axioms required. Why is L2 a Hilbert space? First, it has a valid inner product, which induces a norm and a geometric structure. Second, it is complete. Any Cauchy sequence of sequences in L2 will converge to a sequence that still satisfies the square summability condition. That is why L2 is also a Hilbert space, despite being infinite dimensional. Let's wrap up today's lecture. We started by asking a simple but deep question. What does it mean for a space to be complete? We saw that Cauchy sequences are key to this idea. Sequences that get arbitrarily close to themselves but do not necessarily have a limit inside a space unless it is complete. This brings us to the importance of completeness, especially when dealing with infinite dimensional spaces, where convergence cannot be taken for granted. And finally, we introduced the concept of Hilbert space, an inner product space that is complete. This structure enables us to do geometry and analysis in a rigorous and reliable way, even when we are working with infinite sums, function approximation, or quantum states. Thank you for watching. Please thumbs up and subscribe to my channel.